let's get started. So this is going to be chapter 20 and lab combined. Chapter 20 deals with electrochemistry. Electrochemistry deals with redox reactions, and redox reactions we can use to generate or store electricity. Or store. When I say electricity, I'm talking about energy. You know, chemical potential energy that can be converted into electricity. So let me just write energy here. So generate electricity, store electricity. Also, we can use electricity to drive non-spontaneous reactions. Like, rather than coupling the previous reaction with a alternate, like the hydrogen, you know, the hydrogen attacks the oxygen. Rather than doing that, we could couple that reaction to a power supply, force that reaction to occur. And the first two, you know, generating electricity and storing electricity, those involve a setup, an apparatus called a voltaic cell. There are other words for voltaic cell. For example, people call them galvanic cells. Is there another word for galvanic? We'll just leave it at that. When electricity is used to drive non-spontaneous reactions, the apparatus that we use to do that is called an electrolytic cell. And so today what we're going to do is we're going to build a voltaic cell. You know, how can we generate electricity? Storing electricity we'll talk about as well. All these cells are called electrochemical cells, whether they're voltaic or electrolytic. Electrochemical cells. And so that's what chapter 20 is about. These electrochemical cells. All right, let's look at generating electricity in a redox reaction. And so the first reaction we're going to do is this. We're going to take some copper 2 solution. So we got copper 2 ions in here. We also have sulfate ions in here. One of the chemical properties of copper 2 is it's a pretty good oxidizer. You know, it's a moderate oxidizer. It's not the most powerful on the list, but it's not the weakest either. Sulfate is a good oxidizer too in the presence of acid, but we don't have any acid present here. And so the primary oxidizer will be copper 2. Copper 2 wants to take electrons. Well, metals have electrons, and metals are good reducers. And so what we're going to do is we're going to put our chunk of zinc here. This is zinc solid. Zinc solid into our copper 2. And so what you want to do is you want to pour off a little bit of the copper 2 into another beaker. Not all of it, just a little. And then get your strip of zinc and then just dump your zinc in here and see if you get a reaction. So let's try that right now. Yeah, what's happening? Do you see something happening? It's turning black. What's happening is the copper 2 is attacking the zinc. When it attacks the zinc gets converted into Zn2+, and the copper gets converted into Cu solid. And so the black coating that you see on the zinc are tiny crystals of copper. Tiny crystals of metal look black due to the way they interact with light, visible light. As those crystals grow bigger and bigger, they'll start to resemble orange copper crystals. And so the net reaction here is that copper solid, no, sorry, not copper solid, copper 2 plus aqueous plus zinc solid yields zinc 2 plus copper solid. That's the reaction that's occurring here. This is called the net redox reaction. The net redox reaction can be split up into half reactions. One of the half reactions is called the reduction half reaction. And so if we look at the reduction half reaction, copper 2 plus is reduced by gaining 2 electrons to form copper solid. Okay, so in other words, copper 2 is reduced. This is the reduction half. Well, where did those electrons come from? Well, they came from the oxidation half. And so the oxidation half reaction is zinc solid gives up 2 electrons in forming zinc 2 plus. And so essentially what we have is we have 2 electrons transferred in this reaction, but the electrons are transferred directly here. And so electrons transfer directly. And a redox reaction is often called an electron transfer reaction. Or electrons being transferred from the reducing agent to the oxidizing agent. All right, so the way we can generate electricity is don't let them be transferred directly. What we want to do is we want to transfer them indirectly through a wire. And so the way we can do that is by setting up a cell. And so let me sketch it out right now. So go ahead and take out the the zinc bar from the copper solution and wipe it off with a paper towel. All right, we're going to set up 2 beakers for our cell here. In one beaker, we're going to have the copper 2 plus solution. There's also sulfate present here. And then what we're going to do is we're going to stick what we call an inert electrode. Inert electrode in here. The typical inert electrodes are made out of gold, platinum, graphite. You know, we want something that, you know, gold, platinum, graphite all conduct electricity. And so we want something to feed electrons to the copper 2. The copper 2 needs to consume 2 electrons. But we don't want the copper 2 to take the electrons from the electrode. And so the job of the electrode is just to supply electrons to copper 2. Therefore, we want something fairly unreactive, like solid gold or solid platinum. These 2 are expensive. Graphite's cheap, so we could use graphite. Or we could use, what else could we use that's not so expensive? More expensive than graphite, but a lot cleaner. That is copper. Because if we have copper 2 and copper in a tug of war for electrons, who wins? It's going to be a tie. The other advantage of using copper is if we deposit black crystals of copper on copper, then it stays pure. If we deposit black crystals of copper on graphite, then we get a mix, a heterogeneous mixture, right? Which we'd have to separate to get pure. And so this is an advantage of using copper, and that's what we're going to use. We're going to use copper on this. But copper 2 plus will not oxidize copper metal. And so what we have to do is we have to attach this electrically to the zinc. And so over here in the other beaker, I'm going to stick the bar of zinc here. Solid. And we need to attach this with a wire. And so what I'd like you to do is I'd like you to create a jumper wire. So just pull off one of the wires, either the red one or the black one, and then put 2 alligator clips. We have banana plugs here. Put an alligator clip on both ends, and then clip one end to the copper bar in the copper solution, and then clip the other end to the zinc bar. The zinc bar is going to go into an empty beaker. Empty beaker. And so copper is a good conductor of electricity. Do you know what the jumper wire is made out of? Copper. Copper. And copper can be thought of as a sea of electrons. Have you ever heard of that? Yeah. And so what's going to happen is the copper 2 is an oxidizer. Copper 2 is looking for electrons. Copper 2 is going to come over here and try to pluck 2 electrons off here. Will copper 2 successfully oxidize copper metal? No. And so we're going to make this one out of copper here. But when it pulls on these electrons, the electrons form a chain like this. And when it pulls on these electrons, it's going to tug and continue to tug until it can tug the electrons off an atom. It's not going to be able to tug it off copper, and so this chain is going to go all the way to zinc. And so here, zinc can lose 2 electrons to form Zn2+. Correct? So this is what we have. Actually, we can do without those since nobody's doing anything. All right. So do you see now, did you connect the jumper wire to both? Go ahead and connect the jumper wire to both. And see if you see some crystals of copper metal forming on the copper electrode. Actually, we'll need goggles for this. I don't want anything to splash up.
What do like bubbles and stuff happen?
Bubbles, yeah, could happen. All right, now watch the copper carefully. Do you see any deposits form? They should be black. All right, we're going to do time lapse. After a long period of time, you'll notice nothing happened. So this didn't work. This didn't work. Why didn't this work? Because I know that copper 2 is capable of oxidizing zinc. We just saw it, right? Why isn't it working now? It isn't working now because is zinc 2+ stable in air? No, it's not. You know, this should be Zn2+ AQ, right? And so what you want to do is pour water into this one. So rather than generating zinc ions in air that attach to the surface here, we're going to let the zinc go into solution. So we're going from solid zinc to Zn2+ AQ. And the water is going to help stabilize that. And so go ahead and pour DI water into the zinc beaker. All right, now it should surely be working, right? Did everybody do that? Now keep a close eye on the copper. Do you see any black deposits? You know what? It just might be slow. And so rather than trying to visually see this, remove the jumper wire and then reconnect it to your multimeter. Here. Okay, the red lead should go on the top, the black lead should go in the middle. And then attach the alligator clips. And then attach one of the wires to the copper, the other wire to the zinc. And so what we're going to do is, it might just be slow, So what we're going to do is we're going to put a break in here and put our multimeter here. And you know, we're going to switch our multimeter on and then turn it to DCV. DCV stands for direct current voltage. And then turn the dial to 2000 amp, which means the max would be 2000 millivolts. You know what we're going to do? We're going to measure the voltage. Now what the voltage is it's like we got a flow of electrons here, right? And the electrons should be flowing from the zinc over to the copper 2, right? Because the copper 2 is trying to pull the electrons through the wire. And so if we got a flow of electrons, a flow of electrons is like a flow of water. How can you tell that the water is flowing through the hose? You know, one way you can tell that the water is flowing through the hose is to measure its pressure. To measure its pressure, you take the hose and you cap it off at the end. And then you're going to feel the pressure on your palm, right? Like that. Well, this is what a voltmeter does. A voltmeter caps off the flow and then measures the pressure on the electron. That pressure on the electrons is called a voltage. The higher the pressure on the electrons, the greater the voltage. But the thing is, to measure a proper voltage, you can't have any leakage. Just like to measure the proper water pressure, if you cap it off with the palm of your hand and a bunch of water is leaking around the seal, then are you measuring the full pressure? No. And so when we put a voltmeter on here, no electrons flow. But all we're doing is we're blocking it off and measuring how much force is on those electrons, called the electromotive force. All right, so what is the voltage?
1.
1 is noise. If it's a negative 1, the battery's dead. And you'll have to use a different multimeter. Is it a negative 1?
No, it says positive.
Or maybe it's okay. Actually, it's 0 volts. 0 volts means that is copper 2 pulling? No, copper 2 should be pulling. Why isn't copper 2 pulling? And the reason copper 2 is not pulling is because of this. In order to pull, what we're doing is we're generating cations, zinc 2 plus over here. But there's a major problem with that, and that problem has to deal with static electricity and space charge. You know, is generating a huge amount of positive charge in this beaker going to be stable? No. In other words, if I wanted to go buy a beaker full of zinc ions, could I buy it without the cations? I mean, without the anions? Let's say all I want are the cations. I don't want the anions. Is that possible? No, because you would generate too huge of a space charge, which results in too huge of a voltage, which is incredibly unstable. And so this, just generating a few ions here, generates a huge voltage, which is totally unstable, which prevents the reaction from occurring. And so what we have to do is we have to get rid of the space charge here. And not only that, if we're consuming copper 2 ions here to form copper metal, what's happening with the sulfate? Nothing. The sulfate's staying there. That is, we're losing cation, but we still have the same amount of anion. And so in other words, as electrons are flowing this way, the electrons are flowing left to right. This one's getting increasingly negative. The electrons are going here. This one, the electrons are leaving here. This one's getting increasingly positive, and eventually you generate a huge voltage which prevents any further reaction from occurring. And so what we need to do is we need to get rid of the space charge. How can we get rid of the space charge? Well, one thing is we can sprinkle anions in here. But can you get a pinch of anions and sprinkle it into this beaker? No. Can you pipette anions in here? No. And the same thing, we need a sprinkle of cations over here. Well, the way we're going to do that is by using a piece of paper that looks like this. And the cations and anions we're going to use are going to be inert. You know, we don't want any cations or anions that react with this. And so in this case, we're going to use potassium ions as the cation and chloride ions as the anion. And so what we're going to add in here is a strip of paper called a salt bridge. And the salt bridge is just saturated with, let's say, KClAQ. This is our salt bridge. And what can happen is, you know, these ions are mobile. You know, in solution is strong electrolyte. And so the chloride ions can migrate this way, but that's going to generate a space charge, but fortunately that space charge is canceled because the potassium ions migrate this way. And so for every 2 chloride ions that migrate in here to neutralize the Zn2+, 2 potassiums migrate over here to neutralize the SO4 2-. And so leave the voltmeter on there, okay, and make a salt bridge, and then watch what happens when you put the salt bridge in to both beakers here, one end and the other end. Watch what happens to the voltage when you eliminate the space charge. Okay, so here's some potassium chloride. There's potassium chloride back there, and we have the paper back there as well. Yeah, you could use this one if you want. I'm not using it. What kind of voltage did you guys get? A 1,007? That's 1,007 millivolts.
Yeah.
So it'd be about 1 volt. So you need to saturate your salt bridge in potassium chloride solution. All right, so what voltages are you guys getting? Anybody getting a negative voltage? Negative? If you're getting a negative voltage, it's the voltmeter is just hooked on backwards. And so just swap the... In other words, I just disconnect the alligator clips. That doesn't matter. Are you getting positive now? How many volts are you guys getting? 955. This is in millivolts, so 955 millivolts is 0.955 volts. And so when you're getting a voltage like that, you know, the electricity will flow. So if you remove the voltmeter, you'll get electrons flowing. In other words, you'll generate electricity which we can use to power things. And so what you just made is a battery. So let's take a look at the parts of the battery right now. The parts of the battery This wire out here, this is called the external circuit. We don't need the voltmeter. The voltmeter is just there to measure the voltage. But the external circuit is where where we're going to hook up devices like a light bulb or whatever else. And so we have the external circuit. This external circuit is where the electrons flow. But we can't just have negative charge flowing left to right. Electrons have negative charge. So, you know, what we're getting is a whole bunch of negative charge over here, leaving positive charge over here. And so we have an internal circuit to neutralize the space charge. The internal circuit's a salt bridge. And in the internal circuit, we don't have electrons conducting. We have ions conducting to neutralize the charge. And so here you can see the negative charge here is flowing right to left. You see the chlorides? Yeah. The negative charge is flowing in a circular motion. So we got the internal circuit. Now the electrodes are named according to what ion flows to it. And so over here at this electrode is called the cathode. It's called the cathode because the cations are migrating to this electrode. This electrode here is a reactive electrode because zinc is actually a participant in this reaction. And so the electrode's made out of zinc. And it's not inert. It has to be made out of zinc in this case. This electrode is called the anode. It's called the anode because the anions, chloride, are flowing to this one. The net reaction at the anode is this. Zinc solid gets converted into zinc 2+, and then the 2 electrons get fed into the external circuit here. So oxidation occurs at the anode. Oxidation generates the electrons. The electrons flow left to right by convention to the cathode. At the cathode, reduction occurs. That is, the copper 2s are pulling in the electron to form copper metal. And so what pulls or what pushes the electrons through the external circuit? Well, what pulls it is the copper 2 ions. The copper 2 ions are the oxidizers. They're pulling the electrons through the circuit. Zinc is trying to resist that because, you know, zinc is going to have some kind of ionization energy in order to strip the electrons off there. All right, so oxidation occurs at the anode and reduction occurs at the cathode. The net reaction for this battery or this cell is just this. It's just the copper 2 ions oxidize zinc metal to form Zn2+ plus copper solid. So that's the overall. But rather than transferring the electrons directly, like we did initially, we're transferring the electrons through an external circuit. Do you see how that works? Yeah? Okay, good. Good. We're going to leave the voltmeter on there, and we're going to do one more thing today, and that is, over here in this beaker, we put inside here CuSO4AQ. But we also have some ZnSO4, right? ZnSO4, which is a CCS. And so what I'd like you to do is dump out this. What we originally had in here was just DI water. I want you to dump out the DI water, and I want you to replace it with ZnSO4AQ. But before you do that, I want you to tell me what's going to happen to the voltage. If you dump out the DI water here, and instead use ZnSO4AQ, will the voltage go up? Will it go down? Or will it stay the same? Just take a minute to think about it. All right, what do you guys say? Up or down? Down. Down? Stay the same? What do you guys say? Down? Down. Down? Down. All right, well, if it's a guess, it's a good guess because the voltage should go down. If we add ZnSO4, what are we adding to the equilibrium here? more Zn2 plus. If we add more Zn2 plus, is that going to help? Or no, Le Chatelet says it should shift to the left. And so adding Zn2 plus is not a good thing to do, right? Because we're adding product. And so the voltage should go down. Why don't you check it? What is the new voltage? Did it go down? It stayed the same. Yours says -1. It says +1. It just says 1 with 1 sig fig. -1 with 1 sig fig. Your battery's dead. Yeah, that's an error code for battery dead. How about you guys? Did the voltage go down? It went up? Well, no? All right, we're going to see something more dramatic on Thursday when we do this again, because we're going to change the concentration. We're going to be playing around with the concentrations. Now, why would anybody want to add Zn2 plus to this? It doesn't make sense, does it? Why would anybody want to add Zn2 plus to this battery? Because it's just going to make the battery less. So does it make any sense to add Zn2 plus to this? It's going to lower the voltage. So even though you might not have seen it, it will lower the voltage. And the reason that people will want to add Zn2 plus to this is because of this. If you did this reaction under standard conditions, in standard conditions we have a lot of tables of standard conditions. The copper 2 has to be what? Under standard conditions, the copper 2 has to be 1 molar, and the Zn2 plus has to be 1 molar. So in order to do this reaction under standard conditions, we got to add Zn. And in fact, we should add 1 molar here, and then the copper 2 should be 1 molar. And then we have it under standard conditions. And when we have it under standard conditions, we got lots of tables. And so we can compare the voltage under standard conditions that we get with the voltage that we're supposed to get in a table. But do we have huge tables of non-standard conditions? No. And so that's the reason somebody would want to add Zn2 plus to this. Even though if you're going to build a battery, you'd never do that, would you? Okay. All right, can you guys wrap things up? And then we're going to build some more batteries next time.